Hi everyone, hope you're having a great day today. We're going to go over chapter 10.5 and 10.6 together. And our second exam will be this weekend. Again, it will start on Friday and runs until Sunday at midnight. So 10.5 is going to be about solving equations. Now we learned how to graph, we learned what the inverse function is. So now we're going to look at how to solve for equation. Now, this is actually a lot easier than what you anticipated because if you know how to solve for x, you're going to use the algebra properties in order to solve for trig equation. Now, you're going to require a few extra steps in order to solve for this equation, mainly because you're going to have infinitely many solutions because we know that all trig functions are cyclical, which means that they go on to negative and positive infinity. So here, for this first example, you will see that whenever we solve for anything, it's always going to be over the first cycle, which is from 0 to 2 pi, not including 2 pi, and for all solutions. So we're going to see what the difference is and how we solve for each part, okay? All right, so let's look at solving for 2 sine x minus 1. Okay, so just like solving for an algebra problem, we're going to isolate the variable. But since the variable is inside the argument of sine, we have to isolate sine. So in order to solve for x, we need to isolate the trig function with x in it. Okay, so here we need to isolate sine x. So to do that, just get rid of everything. So we're going to add 1 on both sides and divide by 2. So now we have sine x is equals to 1/2. So everything here up to this point is just algebra. So this is where it gets a little bit different, okay? In order to solve for x, we're going to apply the inverse on both. Now, of course, if this was cosine x, then you apply cosine inverse on both sides. So if we do that, we're basically going to get rid of the sine x because they are inverses of each other. They cancel each other out. So we have x is equals to sine inverse of 1/2. Okay, so this is still nothing new. Now here's the part where you have to be careful. The inverse sine exists in the first quadrant and fourth quadrant. Okay, these are the only two quadrants that they exist in. Now, our original function is in terms of sine, not sine inverse. Doing this, applying sine inverse, only help us determine the value that x is equals to. Okay, so now we see that sine inverse of 1/2 will only return one value. And since sine is positive, sine is going to be in the first quadrant. So sine inverse of 1/2 is going to give me pi over 6. Now this is only in quadrant 1. Now remember that we're trying to solve for sine x, okay? That means we have to reflect this to the other quadrant where sine is also positive, and that happens to be quadrant 2. So you will ask yourself, well, if in quadrant 1 this is pi over 6, what is the other angle from here to here that has a reference angle of pi over 6? And that's 5 pi over 6. Okay, so here we have two solutions for the equation sine x is equals to 1/2. Let me graph that for you so you can see what it looks like. We have the graph of sine here from 0 to 2 pi, and part A asks us to find all solutions inside the first cycle, so between 0 and 2 pi. If I were to graph 1/2, okay, you will see that I touch it twice, here and here. And those two locations are in the first and second quadrant. And that value happens to be pi over 6. And this one is 5 pi over 6, which is what we found here. Okay, so again, I'd like to remind you that whenever you are applying sine inverse, it will only return one value. You're going to take that and reflect it to the other quadrant, okay, where it also have that same value. Okay, if this was negative 1/2, then you're going to have it quadrant 4 and quadrant 3. Okay, so this solve for part A. We have two solutions, pi over 6 and 5 pi over 6 for the first cycle. Okay, now if we were to extend this to part B, now how often will this repeat? How often does the answers repeat? Because I want to find out all possible solutions for this equation if there is no restriction in the domain, which means I have to add in 2 pi times n, where n is an integer. Okay, now let's try to understand what this means. The part plus 2 pi times n comes into play when we're talking about cycles that beyond the first cycle here. So let's draw it down here. Oh, that's terrible. Let's see. Okay, so we know the graph of sine looks something like this. Hopefully you can imagine a better graph than this. But if you look at 1/2, there are infinitely many times that the graph y equals 1/2 touches the graph of sine of x. So we're trying to determine all of these solutions here. Okay, so the first one was pi over 6. Now if I add 2 pi, I'm going to get this one right here. If I add 2 pi times 2, I'm going to get this one over here. Okay, so this one is pi over 6 plus 2 pi, pi over 6 plus 2 pi times 2, and so forth. If you go backward, this is pi over 6 plus 2 pi times -1, which is pi over 6 minus 2 pi. So n value here is basically -2, -1, 0, 1, 2, and goes towards to positive infinity and negative infinity. So if I write the equation, this will give me all possible solutions. Okay, so you can see the other solution here is 5 pi over 6 with the same idea. So this is 5 pi over 6 plus 2 pi and so forth. Okay, so part A give me pi over 6 and 5 pi over 6. If you were to write this as an equation, so x is equals to pi over 6 plus 2 pi n, and x equals pi over 6 plus 2 pi, 5 pi over 6 plus 2 pi n, where n is an integers. That will take care of all possible solutions.
We don't have to differentiate between the first x and the second x?
What do you mean? So this is a solution. This is a set.
That's the set. Okay, I see.
Yeah. So this is a set. So both of these are going to be solutions. They just have two different equations. Now, sometime you can actually combine both of these equations into one, and I'll show you that later on. Okay? Any more questions or anything? All right, so you can see here the two equations. Okay, so again, anytime that we have these brackets, this is a set. This is a notation for a set. Okay, they didn't write x equal, but yeah. Okay. All right, so let's look at this one. 2 sine x minus 1. Wait, is that the same problem? Yes, it is. Oh, it's the analytic solutions. Yeah. We basically just looked at the graph for that. All right, so let's look at this one here. So I'm going to give you some pointers on how to solve problems like this. Okay, so let's talk about the warning. Okay. Never cancel a variable. Always factor. Okay, the reason why that is because if you cancel a trig function or a variable, that means that you're going to get rid of some of the possible solutions. And you're going to see that here in this example. Okay, so first we're going to look at what happened when I try to cancel and see what solution I'm going to get. So our problem here is sine x or sine theta, tan theta equals sine theta. Now let's remember that anytime we use x, our answer is going to be in radian. Anytime we use theta, our answer is going to be in degree. So I'll make the note here. Theta means degree. X means radian. Okay, so let's see what happened. You may be tempted to cancel, oh, I can divide by sine on both sides. And just say tan theta is equals to 1 because I'm dividing by sine on both sides. So therefore, theta is equals to 45 degrees in the first quadrant. And then it's also positive in the third quadrant. So theta is equals to 215 degrees. Okay. And then, of course, we can do the plus 2 pi, or not 2 pi, 360 degree n. All right, so this is going to be our solution, the set for all of the solution. If we would just want the solution between 0 and 2 pi, it's just 45 and 215. Okay, however, that's not correct. Now, this is not all the possible solution because you cancel the sine theta. Now, the correct way of doing this is to factor. So to do that, we're going to bring sine to one side. Now we're going to factor sine out. Okay. Now we can set each one of them equals to 0. Now we still have the solution that we have over here. Theta is equals to 45 degree plus 360n and 215 degrees, 360n. But the solution that you cancel out is this one. Sine theta is equal to 0. So here, theta is equals to 0 and 180 degree. So you're actually missing out 2 of the solutions. Okay. Now, if I were to write this as an equation, I'll have 0 plus 360 degree n, theta equals 180 plus 360 degree n. Well, you will know that the difference between 0 and 180 degree can be combined because they only differ by 180 degree. So if I say theta is equals to 0 plus 180 degree n, this will take care of both of these. And again, you don't really have to write 0 here. Now, we can actually do the same thing with tangent here. So you're going to see the first quadrant, we have 45 degree here. The third quadrant is 215 degree here, but the difference between these two is 180 degree. So I can combine both of these. Is theta is equal to 45 plus 180 degree n, which will take care of all of the solution of both of these sets. Okay, so you can only do that if they differ by an angle that keeps repeating. Okay, so normally it's like 100 degree or 90 degree or something like that. Okay, so here our final solution would be these two equations here for all possible solutions. Now, if I were to list them all out between 0 and 2 pi, we have to do this. So we have to let n equals to 0, 1, 2, and so forth. Okay, so if I let n equals 0, let's see what happened. I have 0, 45 degrees. If n is 1, if n is 1, I'm going to have 180 degree, and 180 degree plus 45, which is 215, right?
Professor, that's 225, isn't it?
Oh, shoot, thank you. Yeah, 225. Now, if I let n equals to 2, let's see what happened. If I let n equals 2, 180 times 2 is already 360 degree. Okay, so that means I'm already going to be over my restriction from 0 to 360. So I do not need to do it for n equals 2. So my fourth solution would be this. Any questions?
So to reiterate, you only did n equals 0, 1, 2, whatever in order to test out whether these answers are within your specified interval?
Exactly. Right. So later on, I'm going to show you how do we know how many n to use. But I mean, you just basically plug in n until you are over the interval that you're supposed to be bounded in. Does that make sense?
Yes, that makes sense.
Okay. Now let's go to the next example. And let's try this one. I'll give you a second to try this. Okay, so we learned this in college algebra. I'm not sure if you remember. This is in quadratic form. So quadratic form is ax squared plus bx plus c. Okay, so our x here is equals to tangent x. Okay, so can I factor? So let's imagine that we just have x here. Okay, can I factor this? Well, we can factor this to x plus 2, x minus 1 equals 0. And I can solve this, x equals negative 2, and x is 1. Well, here I let x is equal to 10x, so I need to substitute that back in and solve. Okay? So what is x equal to? That equals to negative 2. When is 10x equals to negative 2? What quadrant is that going to be in? Nobody?
It's going to be in quadrants either 2 or 4.
quadrant 2 and quadrant 4, right? So now we can get two solutions from here. So for what value of x will give me -2? This is where you can use your calculator, by the way. Everyone got it?
The arc tan -2.
Yeah. What'd you get? Yeah, type that in your calculator and see. Nobody got it?
I got a -1.107, and that's in radians.
Mm-hmm. Yep, that's right. So the first one that we got was pi over 4, right? Because tan inverse of 1 was pi over 4, and it also is in the third quadrant, which is 5 pi over 4. So this right here is when tan x is equal to 1. This part right here is when tan x is equal to -2. Okay, so you can see here we this is an approximate value because tan x of -2 is not an exact value that we can get. Okay, so we have 4 solutions here. Is that okay? All right, so let's look at the second part where it changed to a greater than sign.
Hey, Professor, can we go back? So, I mean, I see what the paper said, that they had to add pi when it was tan x equals -2, right?
Yes.
But for tan x equals 1, we don't have to add any pi afterwards because it's already contained within the interval, right?
Oh,
So it's
okay.
not like
Great question.
pi over 4 plus pi.
Well, we did add pi. Like we add pi from here to get to here.
Okay.
Yeah.
But nothing subsequent to 5 pi over 4 because it's no longer within the interval.
Exactly. Yeah. If you add another pi, you're gonna end up in beyond the 2 pi.
Okay, so to derive the 2.03, right, it was the the tan inverse of -2 plus pi.
Mm-hmm.
Okay, I see it now.
Do you know why that is?
Is it because it's cyclical within pi?
Okay, so let's think about this. Tan inverse is in what quadrant? I'm sorry, tan inverse of -2 is in what quadrant?
Tan inverse of -2. So tan inverse, the restricted domain is from -pi/2 to pi/2.
Right.
So
That's
if it's
quadrant 4, right?
negative, yeah, it's quadrant 4.
All right. So what they were giving us, the solution when you type in your calculator is going to give you a value that's in quadrant 4. Okay. Well, we have to and it's actually negative because it's a negative rotation. Okay. So we have to put it in quadrant 2 and quadrant 4, but not the negative rotation. So what they did is they add pi to go from here to here. That gives you the first answer. And then they add 2 pi to get to this answer, if that makes sense.
Kind of. I was wondering about that when I was doing homework over the weekend. Can you explain to me, so when we give the answers, it always must be in a positive rotation?
Yeah, because the restriction was from 0 to 2 pi. That's our restriction.
Oh, okay,
Right?
okay.
This value right here, this angle right here is not in 0 to 2 pi. It's negative. So it's actually going clockwise. So it's in quadrant 4, but it's going clockwise. So it's not in here. That's the
Got
reason
it.
why we rotate it. So negative 1.107 is exactly the same thing as 5.176. These two are exactly the same angle. They are coterminal. But this one is in quadrant 4 with a negative rotation, which is clockwise. This one is in a positive rotation going counterclockwise. That's why I have a positive angle. This is a negative angle.
Okay, so I mean, not for this specific problem, but hypothetically, if a problem was given where the interval was shown to have a negative rotation, we would just make sure that our answer would be in that same vein, right? In a
Yes.
negative rotation.
Yeah, but you're never going to see them ask for a negative rotation ever. They're not going to ask you like, find me all the answers from negative 2 pi to 0. They will not do that.
Okay.
Yeah, the standard is 0 to 2 pi. We always want the first positive cycle of any trig functions. Okay?
Okay, I understand. Thank you.
All right. All right, so here they want us to find something that is above it. So here we want strictly greater than 0, so greater than the x-axis. Now since we found these 4 values, basically these are the location of my x-intercept. In order to determine the inequality where the graph is greater than 0, you just have to figure out the interval where it is greater. And you can easily do that by, of course, graphing it. But let's say you don't have access to a graphing calculator. We can do this algebraically. And here's how we can do it. What we need to do is draw this in a number line, and I'm going to label these 4, okay? So I'm going to have pi over 4. Now, it may be easier if you convert all of this to decimal, so go ahead and convert pi over 4 and 5 pi over 4 to decimal for me. Oh, actually, it's right here. The decimal approximate of 5 pi over 4 is 3.9. Okay? What is pi over 4?
0.7853.
0.78. Okay. So we have 0.78, 2.03, see 3.9, and of course these spacing are not correct, but we don't need to know the exact spacing here, and 5.81. All right, so what we need to know, okay, first of all, is that these are the location where the graph touches the x-axis, and you can kind of see here. You have 1, 2, 3, 4. Okay, so I have to test each interval and see if f of x is greater than 0 or f of x is less than 0. So all I need to know is it positive or negative? So you can find some number in this interval here between 0 and 2 pi. So I can choose 1/2, for example. So I can find out what is f of 1/2 give me. And it's going to give you a negative value. Okay, so we don't want that one. So we were looking for all the intervals where it is positive. Okay, so let's look at how many intervals it divided in. 1, 2, 3, 4, 5 different intervals. You can see here 1, 2, 3, 4, 5 different intervals. Okay, and I want all the intervals that are positive. And you can see here that second interval is positive, fourth interval is positive. So my solution would be from here to here and from here to here. Okay, so 0.78 is pi over 4 to 2.03 union with 5 pi over 4 to 5.18. That would be my solution. Okay, and there we go. We have this here. Now you see here that we have to be careful within the interval because this is tangent after all. We do have a vertical asymptotes at these locations. So we have to break the intervals that we have here into 2 so that we can omit that vertical asymptotes. And that is where the vertical asymptote occur at pi over 2 and 3 pi over 2. So these are the two intervals that we have here. You can see pi over 4, 2.03, 5 pi over 4, 5.18. So between those two intervals, we have to break it further because there is a vertical asymptote in those intervals. Okay? Questions?
Professor, I forgot the theory behind it, but on a number line, all those points are inclusive or exclusive?
All these points are exclusive because this is strictly greater than. Now, if this is greater than or equal to, you would include those points.
Okay.
So this would, yeah, so that would become a bracket instead of parentheses.
So they wrote the way that they wrote it. They use parentheses, though, sir.
Yeah, that's right. That means that you don't include the endpoint.
Oh, of course, yeah.
Yeah, bracket means you include, parentheses mean you don't include. Okay? Okay. So here we can use quadratic formula if you are unable to factor. Okay? So when we try to solve for this equation here, we rewrite it in quadratic. And we see here what A, B, and C is equal to. Okay? If there's no number, it's just an understood one. Here's our B, here's our C. So here we can definitely not factor this because my C here is -1 and my B here is 3. So you can't multiply something to get -1 and add to get 3. So we basically just use quadratic formula. Once we use quadratic formula, we can solve for cotangent of x, where we have these two values, and then use arc cotangent in order to solve for x specifically. So here we see cotangent x is negative, and cotangent is negative in the second and fourth quadrant. So if you do cotangent inverse of this value, you should have a number that we can see here. Not that one. What's the cotangent? Here we go. So we can see here that we get 2.84 radian, and we can always add pi n. Now remember that the period of tangent and cotangent is pi, not 2 pi. You can see here this is why they use n pi instead of 2 pi n. Okay? So here we just using the calculator in order to find out what is the value of x. Is that okay? And this is the formula in order how to solve for arctangent, cotangent.
Can you confirm that the pi over 2 there comes from the interval?
This pi over 2 here?
Yes, sir.
Okay, so this is not coming from the formula that we discussed before. This actually coming from the formula that we use in order to find out what is the cotangent of a value is equal to, since we don't have a button on the calculator for cotangent. So we're doing this to convert the cotangent, arc cotangent, to tangent so that we can use the button on the calculator in order to calculate this.
Oh, okay.
Yeah. So remember that this is just a shift of tangent and cotangent is nothing more than a reflection and a shift. So this is tangent. Cotangent is a shift by pi over 2 and a reflection. So you can see here, shift it and then have a reflection. And that's where this formula here comes from. So we actually gave you this formula before. So the any two co-functions have this formula. So yeah. Any other questions? Okay. All right, I'm going to give you some time to try this one here. Sine squared plus sine x minus 6. Very similar to the last one, so go ahead. Raise your hand when you're done. Eric, you have a question? All right, let's see what we got. All right, so we try to factor it out like we normally do. So this is a quadratic. If you're having a hard time trying to see what the factor is, you can just let it be like u squared plus u minus 6. So that you can factor this out a little bit easier. And then substitute it back in when you finish. Okay? So this can be factored as u plus 3, u minus 2. And then just substitute u back in. So here we have sine x is equal to negative 3 or sine x is equal to 2. Now remember that sine only fluctuate between negative 1 and 1. So you can see here that since we have sine x is negative 3 and sine x is 2, we are outside of that range. So therefore, we don't have a solution for this. So therefore, this is no solution or the empty set as your solution. Okay, is that what you got, Aim?
Yes, that's what I got.
Great. Okay, try this one. Okay, so a little hint about this before you start. Now, anytime that you have multiple trig functions that you're trying to solve for, okay, you need to be able to see the identity that you can use in order to solve this problem. Okay, so let me give you some guideline to how to solve for equations. So you want to be able to rewrite equation such that the argument are the same and you want to be able to apply identities such that you only have one trig function to solve. Now, if you can't do that, then if you have to be able to factor them such that each trig function is in each factor, then you set equal to 0. The reason why that is because if I have multiple trig functions, it's going to be very difficult for me to solve for x because I have to be able to apply the inverse function to get rid of that trig function. So anytime you have two trig functions that are different from each other, need to see what the relationship between the trig functions and then apply the identities in order to solve for it. So let's look at this example here and see what kind of problems we have. You have 10x plus square root of 3 equals to secant x. Is that right? Secant x, yeah. Okay. All right, so we know of the identities, okay? 1 plus tangent square is equals to secant square. That's the relationship between tan and secant, okay? Now, I want to be able to operate with tangent square. So that means I need to square both sides, okay? So need tangent square and secant square to use identity. So square both sides. You can do this because now you have an equation. You're not restricted to just multiplying by 1 anymore. So a hint here is that always isolate a trig function to each side before squaring. So if I have, for example, secant on this side and it's set equal to 0, do not square it there because remember that if you square a binomial, a squared plus 2ab plus b squared, the middle term will have a times b, which means that if I have tan and secant on one side and the square root of 3 on the other side, that means that when I square it out, I'm going to have tangent times secant, okay? And that's going to make it more difficult for us to solve. All right, so now when we square both sides, let's see what we will get. Now tangent and secant is already on its own side. So when we square it, let's see what we get. So we are squaring a binomial here. We're going to use this property. So we have tangent square plus 2 times AB. So square root of 3 times tangent x plus 3. So square root of 3 squares 3. Then secant square. All right, so I'm going to pause here and have you think of where to go from here. Look at the hint that I show you and see if you can see anything or how to solve for this. Go ahead and talk among yourself. What do you think? What should be the next step? What was the purpose of me squaring both sides? Mai, what do you think? Eric, what do you think? So nobody here again? Eric, are you here?
Yes, I'm here.
All right, so what should we do next? Can I apply any identity?
Professor, I thought we already applied the Pythagorean identity in order to get this current equation.
No,
So
we did
can
not.
we?
We know that this is the Pythagorean theorem identity. We didn't apply it. We square both sides to get here.
Okay, so then in that vein, could we apply the Pythagorean identity now where we keep the tan squared x, but then we equate the 2 root 3 tan x plus 3 equals 1?
2 root 3 10x. Why is this 1? Is that what you're saying?
Well, that plus 3 equals 1.
Ah, I mean, that's good plan. Now, I wouldn't do that because you're changing this value here. So I wouldn't do that. I would subtract the 10x to the other side and set that equal to 1.
Oh, okay.
This part right here is equals to 1. Because we want to
Okay.
solve for x, right? So we want to get the simpler version. Okay, so now we can solve for x because now we only have one value of the trig function to solve for. Okay, so now we can solve for it. Let's subtract 3. So we got negative 2. And get rid of everything here. Negative 2 over 2 square of 3. That cancels. So we have negative 1 over square of 3. Or negative square of 3 over 3. Okay. So what angle is it going to be in? What quadrant is it going to be in? Let's talk about that first. This is negative. So what quadrant is tangent x going to be negative in? 2 and 4, right? So now let's use the first quadrant. What value or what angle will give me tangent of 1 over square root of 3? Think about your sine and cosine. Anybody?
It's going to be whatever the angle was for sine, cosine, sine. So rad 3 over 2 and 1/2. So where is sine is 1/2? It's going to be, so in quadrant 1, it would have been equivalent to pi over 6. So this is quadrant 2, right? So what was that, 5 pi over 6?
All right, so in the first quadrant, we have this one right here, which is 1 over square root of 3, because it's sine over cosine. So that is pi over 6, but we need it to be in quadrant 2, so yes, pi over 6. And then in quadrant 4, 11 pi over 6, because we're going to reflect pi over 6 down here. And that's it. That's our answer. 5 pi over 6 and 11 pi over 6.
Hey, Professor, so if the question wasn't limited to an interval, but it said all possible solutions, how would we write that in the plus pi notation? It would have been
Just plus
5,
k.
just plus pi k?
Pi n, they use n.
Pi
Yeah.
n, okay.
Yeah, so if they want all possible solution, just do plus pi n.
Got it.
N is an integer. Okay. And you can see here 5 pi over 6 and 11 pi over 6. Ow.
Awesome.
Oh, wait. Only solution is 11 pi over 6. So yeah, we have to plug it back in. Yeah, make sure to check your answers. Oh yeah, I forgot to write this warning here. So warning. Anytime you square an equation, you will introduce more solutions. So always check your answer. And to do that, we just plug it back into the original problem. Okay. And in this example, the 5 pi over 6 did not work. And then these are the suggestions I kind of went over previously. So we can see if it's linear or quadratic. If it's quadratic, you can always use quadratic formula or try to factor. If the equation only have one trig function, then we can just solve for the equation of that one function. But if you have multiple, you have to introduce identities or try to factor it so that each factor only have one trig function. Okay, so that's what this one is saying. Use quadratic formula and then use identities to change the equation.
Hey, Professor.
Yes.
There was a question on the 10.5 homework that I was not able to factor out properly. I just didn't know how to do it. Can you help me out with that?
Sure. Do you have it with you?
Yeah, I have it up right now, so I can
Okay,
tell it
go
to
ahead.
you. Cotangent x plus 1, it's in parentheses, and then parenthesis root 3 cotangent x minus 1.
Is the x plus 1 in parentheses?
Yeah, no. So it's in the amount of cotangent x plus 1 is in parentheses.
Oh. Cotangent x plus 1, and then what?
That's correct. And then in parentheses, root 3 cotangent x minus 1, end parentheses.
Cotangent x
Minus 1.
minus 1. And this is equal to 0?
Yes. Oh, wait,
Well,
no,
this
I'm
is
so
al-
sorry.
this is
That one. That one I solved. I'm so sorry. Give me a second.
Yeah, this is already factored for you, so just set
Yeah,
equal. Let me
yeah.
go to 0.
Sorry, I saw that one. This is the one I have. Okay, are you ready?
Go ahead.
2 sine x plus parenthesis 2 plus root 2 close parenthesis equals negative root 2 cosecant x.
So did I write right?
2 sine x plus anything equals negative root 2 cosecant x. Yes, sir, that's correct.
Okay. Let's see. So cosecant x here, we can change that to sine, so 1 over sine. Let's see. See, we can get both sides. So this part right here is the one I'm concerned about.
Mm-hmm.
The 2 plus square root of 2. Let's try squaring both sides. So sine x plus 2. I want to get rid of this square root. So I have negative square root of 2 cosecant x minus square root of 2. Okay, so let's square both sides. So I'm going to have 4 sine square plus 4 is 8 sine x plus 4. equals to 2 cosecant square x. Square root is positive times 2. So 2 times 2 here is 4 cosecant x minus 2. Okay. So now the big problem here I have two separate trig functions that I need to be able to combine somehow. But nice thing is that they are actually reciprocal of each other. So I can actually multiply, find the reciprocal. So 1 over cosecant, which is sine square x, plus 4 over sine x minus 2. And I can probably combine some values here. So let's bring this one and this one. That would give me 6. And I can probably multiply each one of them by sine square. So I'm going to multiply both sides by sine square so I can get rid of this sine square. So let's do that. So if I do that, I'm going to have, let's see, 4 sine to the 4th plus 8 sine cubed plus 6 sine square. And here I just have 2 plus sine. All right, so let's bring everything to one side. So now that I have everything in terms of sine, except this one here. So let's see if I can factor this here. I have 5 now. Let's see. Someone tell me that's not correct.
Did you get the, so I know you subtracted 2 or subtracted 4 to one side, and you wrote
Oh,
down
that's gone.
6.
That's gone. Yeah, thank you. Okay. Yeah, I thought I had an extra values in there somewhere. Yeah, so the 2 should not be there, right? I canceled the 2 already. Thank you. Get rid of that. So now this is better. Okay. All right, so it looks like I can take out a sign, but let's see if I can factor by grouping. So I can take out a 4 sine cube here. So that leaves me with x plus 2. Is that it? Oh, wait. Did I mess up something?
So that -2 over there, when it goes to the left-hand side.
That should be 8, right? Wait. 8 or 4? It's 4, right?
It shouldn't be, oh, hold up. Cosine 2 is 2 over there.
Oh, no, the 2 came from, the 2 should still be there because I should have skipped this step right here. Because this times this cancel the sign out and leave the 2. This is still a 4. This times this give me a 4 sine. Yeah, so this would be 4 sine.
My question, sir, is what happened to that -2 in the circle that you circled?
This one right here?
Yeah,
I
what happened
combined
there?
with this one to get 6.
But it's a -4 on the left-hand side. Shouldn't that be a 2, sir? So it's -4 plus 2.
Ah, yeah. Thank you.
Yeah, so.
Yeah. And then, should this be a 4 then, right? Yeah, it's a 4 because this is a 4 right here. Okay.
Yeah.
All right, now we're good. Then should we plus? Let's see. I think this should also be a plus. Did I miss something? I think that's it because I can copy this sine x over plus 2 and I can factor out 2 sine x. Yeah, I think that works now. All right, so we have sine x plus 2 times 4 sine cube plus 2 sine x. Now you can set that equal to 0 and solve. Okay, so sine x is equal to negative 2, and that doesn't work. 4 sine cube plus 2 sine x equals 0. And looks like we can take out some more stuff here.
Take out 2 sines,
2
right?
sine. And so we have sine square plus 1. So here we have 2 sine x equals 0 and sine square equals negative 1. So we can find a solution for that one. So x here is 0 and pi. This one right here. Notice that it's plus or minus, and we cannot have this since it's square. So there's no solution on this one either. So I guess that's your only solution.
Okay.
Okay.
All right, thank you.
Let's look at, yeah, we have time for the last section as well. So. Okay. Okay, so this is pretty much the same thing as we've been doing. So I should not have done that. Let me get rid of all this. All right, here we go. All right, so now we're going to introduce more identities with double angle formula. Okay, so I'm going to add to the list of how to solve a trig equation. Now, I actually mentioned this before, which is the first one. We write the equation such that the arguments are the same. Now you can see here in our first example, the arguments are not the same. This argument is 2x, this argument is x. So we need to rewrite it by expanding using the double angle formula. And we did this here. Now, why did we choose this one? Now, cosine, double angle for cosine have 3 choices, right? Cosine square minus sine square, 2 cosine square minus 1, and 1 minus 2 sine square. We choose this one because we already have cosine on the other side. I do not want to use this one because there's cosine and sine. And remember, we always try to keep only one trig functions. And the same thing here. I don't want to introduce sine because I already have cosine on the other side. So we bring it to one side and we factor, and then just solve like we normally do. Okay? All right, let's look at an example here. All right, I'm going to allow you to try this, and then we'll go over it. All right, so if you recall the guideline, we want to only have one trig function. Well, the problem here is I have two different trig functions multiplied together. But you do realize that this is actually the double angle formula, cosine x sine x. So this is equals to sine of 2x. Well, we have this extra 2 here that's making this a 4, but we don't have to use that. So we can rewrite it as 2 times 2 sine x cosine x equals square root of 3. So here we're going to apply the double angle identity for sine in order to combine this so that we only have one trig function to worry about. From here, then we can isolate the variable and then solve like we normally do now. Now here is the extra step that you have to do. Here we are dealing with 2x, not just x, okay? So here we have sine 2x, we have a positive value, so we know that this is going to be in quadrant 1 and quadrant 2. But we're going to set 2x is equals to this. Now, square root of 3 over 2 in the first quadrant of sine is going to equals to pi over 3, or 60 degrees. Reflect that over to quadrant 2, then we have 2 pi over 3. But don't forget your 2 pi n. Now we need to solve for x by dividing by 2 or multiplying by 1/2 to each term. This will give me x is equals to pi over 6 plus the 1/2 times 2 give me pi n. And that is my first equation. Same thing over here. I can multiply by 1/2. And I will get pi over 3 plus pi n. Now, you see what happened here is that when I start out my quadrant 2, okay, but this answer right here is actually now in quadrant 1, okay? So be aware of that. We have to start where the quadrant was positive, and then you can solve for x specifically. Because remember, if I take an angle theta, I'm going to times 2. That part is in quadrant 2. Okay? We didn't say that x is in quadrant 1 and 2. We said that 2x is in quadrant 1 and 2. Okay? All right, so my final answer for both of these will be pi over 6 plus pi n and pi over 3 plus pi n. Don't forget, n is an integer. Right, questions?
Would that have changed? Would the way that we solved that have changed if it wasn't an equality, but it was an inequality where it was greater than or less than root
Yes.
3?
So for equality, you're going to have points. For inequality, you're going to have intervals.
Oh, yeah.
Does that make sense?
Yes.
Because for equality, you're finding the zeros when it touches the x-axis. But for inequality, you're finding the interval where it is above the x-axis.
Okay, okay.
Yeah? Okay. All right. So now, let's find out all the solution between 0 and 2 pi. So now that we found the two equation, okay, I told you before that we need to let n is equal to 0, 1, 2, and so forth until it's over the 2 pi. Now, how many times do we have to do it? Here's the trick. This 2 right here, this 2 is my b value. Remember? Right? Sine of 2x, this is my b value. This dictates how many n you're going to use. So remember that n start at 0. So that means I need to use 0 and 1. That is 2 value of n I'm going to use. I'm not using n equals 2. I'm using 2 values of n. That's different. because n starts at 0. All right, so let's try it and show you why. So when n is equal to 0, I'm going to get just pi over 6 and pi over 3. If n is equals to 1, I plug 1 in here, so I have 7 pi over 6 and 4 pi over 3. If n equals to 2, let's see what happened. If I plug 2 in here, I'm already going to have 2 pi. 2 pi plus pi over 6 is already over 2 pi. So therefore, I cannot use n equals 2. So this would be my solution. Does that make sense? And there's your 4 solutions here.
So then using your hint about the b value, right? Suppose it was sine 3x. So we would use the 3 values of n there?
Yeah, you use n equals 0, 1, and 2. Now, I'll show you why that is. Now, b is equals to the number of complete cycle within 2 pi. That's what b represents. And I'll show you why that is. So if you have sine of x is this, okay? This is just sine of x. Now, sine of 2x means that you're going to have 2 complete cycle. So you're going to have something that looks like this. You're going to have 2 complete cycle within 2 pi. Now, if I want to find out if it equals to some values, you can see here, I have 1, 2 solution for just sine x. But if I'm looking at the red one, the intersection, I have 4 of them. So it doubles the number of solution I have of the original function, of the original sine x. Does that make sense?
Okay, that does, sir. And can you help me isolate where you got sine 2x from? Because you got it after you derived the double angle identity, right? So
Yeah.
2 times 2 sine x,
Yeah.
2 times sine 2x, and that's where you got the b value.
Yes.
Okay, I get it.
Okay. All right, so of course you can use the graphing calculator to confirm this. Okay, here we go. Let's practice this one. So use that hint that I told you earlier. Tan 3x plus secant 3x equals 2. All right, let's look at how we did this. Does anyone want to share what they tried? So I can see if I can help you guide you.
Okay, I can try sharing. I didn't finish it, but I can try sharing.
All right, so let me write it down first. All right, so we have 10 at 3x. Was it plus secant 3x?
Yes. Yes.
And then
Equals
what?
2. Equals 2.
Equals 2?
Yes, sir.
All right, so what did you try?
So I know that the relationship between tan and secant is that they both share a cosine denominator. So I just wrote it in terms of sine and cosine. So tan x becomes
Okay, hold
sine.
on. Before you start, if you do that, you're going to introduce, okay, so tangent is sine over cosine, secant is 1 over cosine. So that's fine, okay? Now you can combine that, that's fine. However, the problem you have is you still have two trig functions. That's the problem.
Okay.
Okay? Actually, let me see where you got from here.
Well, where I go from there is to get rid of the denominator. I multiplied cosine on both sides to get rid of the denominators.
Sure. Okay, so now you have sine 3x plus 1 equals to 2 cosine 3x. Okay?
Okay. And then
Now what? Now you have exactly the same thing as you did before. You still have two trig functions. Can
yeah,
you
that's
factor it somehow?
um I don't know how yet.
So is this where you're stuck at?
Yes.
Okay. So let's remember all of our trig functions that we have 1 plus tangent square is equal to secant square. Now, in order to get the square, I need to square both sides. And I told you before that do not square both sides when you have two trig functions on the same side. So you need to bring one of them to the other side. Okay, so let's bring secant to the other side. And now we can square both sides. So this becomes tangent square 3x plus 4 tangent 3x plus 4 equals to secant square 3x. Okay? All right, so now we can combine to get only one value, one trig functions. So if I take secant and I subtract tangent on both sides, so you can see that 1 is equals to secant square minus tangent square. So I can
Professor,
subtract tangent square.
I'm sorry. I'm getting confused. From your first line to your second line, tangent 3x plus 2 minus secant 3x. I know you brought the 2 over to the left side, but that should be a minus 2, right?
Oh, I'm sorry. No, did I bring it over? Oh yeah, I did. I guess I didn't have to do that, but yeah. So let's do that minus. Okay,
Or
then
or
this
just
should be the minus.
because you meant to have each side have its isolated trig functions, right?
Right. Hmm.
Okay.
Yeah, it doesn't matter which side the 2 is on. But yeah, I guess I can do it this way. But it doesn't really change anything here. So that cancel. So secant square minus tangent square is going to equal to 1. So now I have negative 4 tangent 3x minus 4 equals 1. So now let's solve this. Plus 4 on both sides. Okay, let's get rid of this 4. Negative 5/4. Now we need to use our calculator to find out what is tangent inverse of negative 5/4 is equal to. But before we do that, let's determine what quadrant tangent negative is going to be in. So that's quadrant 2 and 4. So 3x is equals to tangent inverse of negative 5/4. What value is that?
I got Negative 8.96.
Negative 8.96. Now
Sorry,
this right here,
0.896. I'm sorry, 0.896.
0.896. Negative 0.896. All right, this right here is in quadrant 4, but it's going counterclockwise. Okay, remember that tangent is either in 1 or 4 for tangent inverse. So in order to get it to quadrant 2, I have to add pi to that. So go ahead and add 3.14 to that.
So positive 2.24.
All right, and now we're going to add another pi to get to the 4th quadrant. So 5.38.
Yep.
Yeah. All right, so that is my 2 values. Now we need to solve for x by dividing that by 3. So what we have at the end, x is equals to, what's 2.24 divided by 3?
0.746.
746, and then this one over here,
1.79.
1.79, and that's our 2 solutions inside 0 to 2 pi. All right, let's see if we did it right. All right, and we got that. All right, so we got the, to get the first one, 2.14, right? I mean 0.214. And then what was the other one? I moved the value. I forgot what it was. What was it? I think I accidentally moved this. Anyway, so here we have 6 answers. Now these 2 right here are only the first 2. Now I told you that my B value will kind of determine how many solutions we're going to have. So here B is equals to 3. That means we're going to have 3 times the normal answer we're going to have between 0 and 2 pi. So normally we only have 2 solutions, but here since B is 3 times 2, we have 6 solutions total. So our first one was x is equals to, is it 2.14? No, 0.214. 214 plus pi n. And then the other one, x is equals to, what was the other one? I don't remember. Aim? What was 5.38 divided by 3?
Hello, I'm sorry, I had a phone call. 5.38 divided by 3.
1.79
Yeah, 1.793.
pi n. Yeah. Okay. Any questions?
So I know that the B value is 3, right? But then the total subset of answers, there were 6 answers. Is
Yes.
it because for that 3 from the B value, we had to apply to both quadrants, 2 and 1 and 4?
Yes, of course.
Okay, I get it.
Yeah, so if you're doing just the equation, okay, we have 2 equations, but now instead of we have to plug in n equals to 0, 1, and 2 for a total of 3 total, right? 3 total n values. So when you plug these 3 in there, you get your 6.
Got it. Okay, thank you.
All right. Let's see. All these downs here are application problems. All right, try this one. So this is exactly how we solve for double angle. This is just half angle. All right, are we done? Nicholas, any problems? Yeah, looks like y'all not in here. Okay, let's solve 2 sine x over 2 equals 1. So I'll bring the 2 over. All right, so sine is equals to 1/2. So this is going to be in quadrant 1, since it's positive, and also quadrant 2. So now we're saying that x over 2 is equal to sine inverse of 1/2, and that is pi over 6. Reflect that over to quadrant 2, we have 5 pi over 6 plus 2 pi n. Now we can solve for x by multiplying both sides by 2. All right, so that will give me x is equals to pi over 3 plus 4 pi n. Now, since the b value tells us that we're going to have the number of complete cycle in 2 pi, notice that the b value here is 1/2. So that means we're going to have half as many answers as we would if we were to have it originally. Same thing over here. We're going to multiply by 2. 10 pi over 6 plus 4 pi n. All right, so now if I want to find out all solutions between 0 and 2 pi, or I would have to plug in n value. So let's say n is 0. That means I have x equals pi over 3. And 10 pi over 6, which reduced down to 5 pi over 6. Now, if I plug in n equals 1, that's going to be 4 pi. So that's already over 2 pi. So I only have one solution for each equation. And that would be it. And if I want to solve for all solution, I would give these 2 equations. All right. Okay, so you see here we have 5 pi. Oh, 5 pi over 3. I'm sorry, not 5 pi over 6. Because it got reduced by 2. All right, so now let's look at inequality. We're going to do it like we did before. If I were to solve for 2 sine x over 2 minus 1 to be greater than 0. Oh, wait, this is solving by graphing. Never mind. And this is music tone, so an application. And this would be our last button. Okay, so the basic component of a music or a pure tone is that the graph of the model of the sine pressure is y equals p in pound per square foot of a pure tone at time x equals t in seconds. The frequency of a pure tone is often measured in hertz. 1 hertz is equals to 1 cycle per second and is abbreviated Hz. What is the frequency of the pure tone of the graph? Okay. So 1 hertz equals to 1 cycle. So we can count how many the peaks are in order to determine the frequency of the tone. So we have, let's see, how many full 1, 2, 3, 4, 5, 6 cycles total in 0.04 seconds. So if we take that 6 divided by the 0.04, we have 150 cycles per second. So we have 150 hertz of the pure tone. Let's see. think that's it. See the time to cover one complete cycle. Well, since we did 6 cycles in 0.04, we just have to divide that. So by 6 to get the period for 1, and so we got 0.006 repeating for a period. And then use a calculator to estimate all solution to the equation y2 equals 0.004. Okay, so that means that we want to find all solution to this. So let me show you how to do this on a calculator.
Professor, can we do this on class calc?
Oh yeah, you can. Yeah, let's do that. Yeah, I wonder if I can actually find intersections on here. So I haven't used this yet. So okay, so let's try it. All right, so let's type in the equation. We have 0.004 sine 0.004 sine of 300 pi x. All right, so let's try to zoom in here. It's going to be a pretty small graph, so.
Oh, okay.
Yeah, it's a pretty small graph. So the graph that they showed us was 0.04 with x. So yeah, it looks something like this. So what they want is if we were to graph another function, y equals 0.004, and then they want us to find out the they want us to find out the intersection. So let's zoom in and see what that is. So it looks like it intersects at the top of each one, and we can actually find out what that is. See if I can find the intersection here. Yeah, I actually don't know how to do that on here. I don't think that's the function for that. Yeah, I don't think there's a function on it to find the intersections. But let's see if we can take a guess. So this is 0.001. It looks like it intersects right around here. Yeah. So 0.12345. So since there's 5 spaces, I'm gonna guess 2, 4, 6, 7. 0.0017 is the first one.
Yeah, it's pretty close. So the way that I did it, Professor, is for the top equation, for the sinusoidal wave, I also declared that as a function y equals. So when you do that, right, when both of them are a function, they will give you points where it intercepts.
Oh, okay. Oh, I didn't type in y equal here.
See, and now a point comes up to the intersection. So
I don't see the intersection point though. Is that it? Is that the point? Oh, right there. Yeah. 0.001666. Yeah, 2/3. Okay. Yeah, nice. Thank you for that. So what was our solution? Yeah, they got 0.0017. Yeah, that's right. Yeah, so basically we can find out what is the period for each one of them, and then we just add that to n. So the first one would be 0.0017 plus the period. Cool. All right, well, we managed to finish both of them. If you want me to answer any homework questions or whatever, let me know.
Okay, give me a second.
Will we have a lecture on Thursday?
I'm sorry?
Will we have a lecture on Thursday?
Yeah, we can, I'll answer whatever, oh wow, it's only Tuesday? Wow, I was kind of rushed through it. We will have a review session on Thursday. If you want me to do any problems on the review or on homework or whatever, then just let me know. So maybe a short session instead of a full 2 hour.
Nice, okay.
Okay.
Professor, can you clarify a term for me? So I know in the review sheet, right, on number 1, you said state the domain restriction and the range of an inverse function. So that wording for me tripped me up because it was my understanding that the restriction is the range of the inverse function. Is that not correct?
Yes, that's correct. So I'm talking about, okay, so for example, let's look at the domain and range for just sine. So the domain of sine that we need to restrict it to was from negative pi to, no, negative pi over 2 to pi over 2, right?
Yes.
So that's our domain restriction. And then our range isn't really a restriction. Range is negative 1 to 1. So for sine inverse, this is what I'm asking for. So this is negative 1 to 1. And then the range is negative pi over 2 to pi over 2. So you need to know this. Well, in order to know this, you need to know this. So you see how they just switch?
Yeah, and I know that for inverse functions, right, there are two funky ones. I think it was tangent and cosecant. Is that right?
What about?
Because it's disjointed, right? So the range is from like negative infinity to negative 1 union 1 to positive infinity. Is there some kind of relationship there to the other, I'm sorry, to its parent function, or it's call it a cosine or sine relevance?
They only share one point in common, which is the maximum and minimum of its reciprocal functions. But other than that, it's the opposite. Sine and its reciprocal are opposite range. They only share the minimum max value.
Okay, I think I had the question better. Sorry, up here. Um, for the functions that have an asymptote, right? That asymptote is basically inverse. So whatever function had a vertical asymptote, it becomes a horizontal asymptote,
Yes,
right?
that's true.
Okay, and then at that point, horizontal asymptote is where the disjoint happens. So
Yeah,
so the domain or the range can never happen there.
right.
Okay, I get that concept. Can you help me solve for number 2? I got the answer, but it was just I'm not confident as to why I got the answer. But number 2, part A, is
Go
the
ahead and read it.
sine inverse, and then bracket sine 4 pi over 5.
Okay. All right, so let's look at where is sine 4 pi over 5 is at. It's right here, second quadrant, right? Well, the thing with this is that sine inverse exists only the
Fourth quadrant.
first and fourth quadrant, right? So this happens to be in quadrant 2, okay? Now sine is also positive in quadrant 2. So that means that what we're trying to do here, okay? Oh, by the way, what answer did you get?
I got pi over 5.
Right. So in order to get the value of it, we have to move this or reflect it to the correct quadrant that the domain restriction is for sine inverse.
Okay.
Because we know that sine 4 pi over 5 is the same thing as saying sine of pi over 5. So we take sine inverse of sine pi over 5. We can say that this is equals to pi over 5. Because sine inverse only exists in quadrant 1 and 4. So we have to reflect it to the correct quadrant before we take the sine inverse. Most people think that they see sine inverse and sine, they're like, they're inverses of each other, so they just cancel and that's it. And then your answer is 4 pi over 5. That's incorrect. Okay? It's actually pi over 5 because my inverse function is on the outside.
Okay. So on that last point that you said, if we ever saw sine and sine inverse of 4 pi over 5, where the sine inverse was the inside function, those do cancel out though, right?
Oh, well, here's the other thing then. When you're saying sine of sine inverse, well, inside here, this needs to be an angle. So you're not going to have 4 pi over 5. You're going to have like square of 3 over 2 or something.
Okay.
Yeah.
Got it. What else was I saying? I was looking for, let's see. Can you give okay, so I know the algebraic expression. So in review number 4, right? I know that was on the homework, but I'd like to review it again too. So this is 4a, which is cosine of tangent inverse. And the inside argument is u over square root of 1 minus u squared. And when we're doing this, right, I think I remember your recommendation. You just said basically draw out the triangle first, right, and just label the sides correctly.
Yep.
So tangent is sine over cosine. So the y is u, the x is 1 minus u squared. Therefore, the r is 1. Oh, there we go, yeah. And then from there, just solve for cosine. So take the adjacent over hypotenuse.
Mm-hmm.
Okay.
Oh, adjacent, not. So it just get 1 minus u square root.
Cool. So that I did that right. Are we expecting 30 questions again on the multiple choice and no graphing, or because there's not going to be any graphing, are we expecting 40 questions on the multiple choice?
No, just gonna be 30.
Just 30. Okay.
So it would be longer. It would be this. It will take you the same amount of time because the equation solving is a little bit longer, and also the proof. So you do some proofing on your sheet of paper instead of multiple choice.
And professor, I mean, I know last time there was a paper restriction. In this case, can I have can I use however much paper I need to use and then just make sure I scan that for you correctly?
Yeah, just use however. You can get more than you need, and then make as long as you label it in the dark marker.
Yes, sir. Okay, I
Do
understand
that before you take the exam.
Got it. Got it. Okay. And inverse version. So there's a
Yeah, so be warned that you will have. I think I'll give 2 proof that you have to write out on your paper. So yeah, you should get more scratch paper than you think you need. So at the minimum, you're gonna have to prove 2 by hand. So just like the graphing last time, you'll be proving it this time by hand.
Got it. And then I was starting to work on 7a before class started, right? And I noticed the 7a is, I'll read it out to you. It's 2 cosine cubed x minus cosine x equals cosine squared x minus sine squared x over secant x. Now, clarification, this would be a proof question, right?
Did it say proof? Yeah.
It says establish the following identity, but I thought that meant proof.
Yeah. Establish identity is proof.
Got it. So I know you gave us a lot of guidelines when we were learning about this and practicing this. With that being said, right, would you allow us a cheat sheet for those guidelines, sir? I'm just going to come out and ask.
No.
Well, I had to ask. Okay.
Yeah, I could try, but no. Yeah, so this right here is it's actually quite easy. It's only 2 steps here. So 2 cosine squared minus 1. So that's why I'm forcing you to memorize these identities so that it would pop out to you. It's like, oh, 2 cosine squared, that's the double angle for cosine, right?
Yeah.
Cosine of
Yes.
2x. But that's also where we need to go to. So that is equals to cosine squared minus sine squared times cosine x, but if you rewrite that as cosine over 1, which is the reciprocal, we take the reciprocal of that, that equals to secant x. Yeah?
You lost me at the reciprocal of cosine. How did you go
Sure,
from there to secant?
sure. So it'll be easier if I start from the right-hand side. Let me show you. So on the right-hand side, I know secant is 1 over cosine, right?
Yes.
So if I take cosine square minus sine square, and I'm dividing by 1 over cosine, which is multiplying by its reciprocal, which is cosine, which is where I need to go here.
Oh, I see. Okay, I get that now. Got it.
Yep.
Okay. And so for the multiple choice sections, so I guess that's the only section for the test, right? Are we going to have 3 hours total now, since you said you would expand the
Yes,
time,
I'll give you
or
3
is
hours total.
okay? Awesome, awesome. And then when we do the document uploading, that's we can email it to you after we finish the test, right?
Yes. So
Okay,
instead of emailing to yourself and then download and then upload again, you can just forward that email to me or just send it to me directly.
awesome. And you want it all still in one PDF file?
Yes, that'd be good. So make sure that the proof that you're doing is the first page.
Okay. And like we did for the graphing page last time, where we had to label the graphing page, do you want to label it as proof page specifically?
You can, but I mean, it's kind of obvious that what you're trying to do should be on the first page.
Yes, sir.
Yeah, but I'll make sure to include that direction when you take your test.
Yes, sir. And then are there any hints for us this time? Since last time it was the first time I took it on the proctorial platform. Is there anything that we can improve this time in order to, I guess, reduce the flags that we got during the review?
Not really. I mean, I watched your videos anyway, so I still need to finish watching those videos.
Okay,
I've
awesome.
been incapacitated,
Sure,
capacity.
yeah.
Yeah.
Co-
For the past like week and a half. So
Yes,
yeah.
sir. Yes, sir. Okay, and then I guess all the homeworks for this test are due on 10/4, right? So 10/1 through
Yeah.
10/6 are all due on 10/4.
Yes.
Awesome.
All great
Okay.
question. I'm pretty sure somebody will ask this again without watching the video.
The possibility exists, sir.
Oh no, I know it. The possibility or the probability of this is 99.9%.
Oh man, that's outside of 3 standard deviations. Okay.
Yep.
That's that's it for me today. I mean, like, if you had any kind of wise words for us to study for the test, right? What do you think should we
Memorize those identities.
memorize those
And
identities, of
then
course?
next thing is you need to memorize that unit circle and then all those values, the specific values, because that's what's going to save you time instead of you having to draw your thing out and everything like that. So as you can see, as we're doing more and more of these solving for equations, you need to be able to identify what is the angle, what quadrant is it in, and what is its reference angle, and how to rotate it, and so forth, and reflect it to the first quadrant to get the exact value. Because you're
So
not going to be able to find to get the decimal answers. All the answers are going to be in exact form. So
are we going to have any questions that touch back onto test one? My underlying question is, should I review test one as well too?
I want to say no, but again, this is math, so you're going to have to know previous section to be able to do this section.
Okay.
So yeah, I mean, it'd be a good if you review it because you should know it because you need to know test one to do test two and test one and two to do test three and so forth. It's kind of compounded like that.
Got it. Got it.
Yeah, it's not like a
Okay.
separation like English or history or something like that.
Okay, sir. Okay, thank you. I mean, I hope I didn't ask too many questions. Those
No,
are just
I
ones that I'm
really,
asking like right now.
I'm happy that you're asking question. I'm pretty sure other students are grateful that you are asking question because apparently nobody is asking questions. It would be a very boring and quick class without you. On behalf of all the other students, thank you.
Oh, well, thank you, sir. That's it for
Right
me for
side,
today.
Nicholas, anybody? Eric, want to speak up?
I guess my last question is for the end of the term, right? At the end of the semester, after you factor out all of our grades, right? I'm just not sure how TCC as an institution does it, but will there be a curve in place, sir?
A
Because my
curve?
university did, yeah, like a curve for our grades. Because like my university, when I was in undergrad, we had curves as well too for our final grades.
I don't see why there would be a curve.
Okay, I
But
understand, sir.
normally, if you are in class and you participate, and I see that you're active, I would be more inclined to help you to the next letter grade if you're close, as opposed to never showing up or not doing anything or stuff like that. So yeah, you will be on the short list of people who I know and remember.
Understood, sir. Loud and clear.